Hello guys, welcome back to my channel, Boy. It's another Simulkuy video, and today I will be talking about heat exchanger specs. Yeah, we will talk about what are the type of specs that we can uh, put inside the heat exchanger model, and also we are talking about what is the function of each spec, how it will impact the model. So yeah, in this simulation, you can use any heat exchanger case. Yeah, but if you want to make it the same with me, uh, I use two components, hexane and also H2O as the working fluid. Fluid package, I use Van Robinson. And for the condition, I'll show you. Yeah, this is the C6 in that going to the shell side, and also cooling water in that going to the tube side. So this is the condition, and for composition, I use pure both hexane and also H2O. This is the current condition of heat exchanger when we fully define our feed stream. Uh, it will show unknown delta P. So now the question is, can we define other parameter to substitute this delta P? For example, is it enough to directly input the temperature for both outlet and then the pressure will be calculated? Let's see. Yeah, for example, this cooling water will be heated up to 40 and the C6 will be cooled down to 120. Yeah, you could see that the solver couldn't solve this problem yet. Now, how if we make it like this? We put 0 here. Okay, so here we could see that the pressure could be calculated, yeah, because we need two information, but still it is not enough. Yeah. Now, if we try to spec this, it will show the overspecified. So we need to erase one of it. Yeah, for example, this one. But you will see that the pressure will missing because in the C6 out, we only have one information. So in other words, we cannot substitute the delta P spec with temperature or vapor fraction, yeah, because this delta P is a standalone solver with the temperature or the heat balance. Yeah, this is actually my guess from what I observed just now. So why I know this, because when I input the temperature and also the vapor fraction, it is not directly connected to the delta P calculation. So for delta P, it is a standalone one. We need to specify either the delta P or the direct pressure of the stream. Yeah, you can put here like 290 and 990. Yeah, or you put the delta P on the parameter stream. Yeah, for example, 10 kPa. Okay. The next thing is we need one temperature spec, yeah, in this condition, or vapor fraction spec. Yeah, let's see. For example, I want to make this as a saturated liquid. Then it will calculate how much the temperature is it, and the cooling water also. Yeah, the rise of cooling water. How if we specify the cooling water temperature rise to 40, then it will calculate the temperature and also the vapor fraction. Okay. So now, is there another way? Then we specify the one temperature spec. For example, how if we don't know the flow rate of the cooling water, it will be calculated. Yeah, it is possible. So for example, I delete this, and then we need to specify two variables. Yeah, because previously one spec is by the flow rate of cooling water, but right now it's deleted. So yeah, we need to specify two. Yeah. For example, the rise of the cooling water become 40 Celsius and the C6 out become 120. Then it will calculate how much mass flow needed. Or if we delete this and specify as 0 for saturated liquid, yeah, we also can calculate how much the mass flow needed. Okay, so I will put back this and put this as 1000. Now, Is there any other way? Yes. So in design specs, yeah, we could see that there are several parameters. Yeah. When we fully define this heat exchanger, we will calculate the UA value. Yeah, UA value is calculated here, but can we specify this UA value? Yes, we can. Yeah, we can copy this and paste to the left side, and then we try to delete CV out temperature. Then we put this as an active specification, and voila, you still can solve this problem without specifying any temperature of the outlet. Okay, take note that the E100 heat balance is a must active spec, yeah, because heat balance should be there inside the simulation of the heat exchanger. Yeah, it's the fundamental of the model. So this is a must, and the second one is the thing that you can change. Yeah, whether you want to specify the temperature or UA, and other thing beside UA, we can also specify. Yeah, let's see. For example, the delta temperature. So, for example, the positive stream is C6 in, and the negative is C6 out. So, what does it mean? So, C6 in minus C6 out. So, C6 in is the largest temperature. So, currently our delta T is 3.4. How if we want it 5? Yeah. Then we move the active spec, yeah, from UA to this. Yeah. Then it will calculate the UA. No, yeah, it's not the same UA as the previous one. Okay. What else? Yeah, we also can rename this, yeah. So delta temperature. This one is UA. Okay, the next one is minimal approach. For the one pass exchanger, yeah, we only have overall. So now, what is the main approach? I will show you during the demonstration. Main approach. The best practice of approach is above 5, yeah, around maybe 10 up to 20. So, for example, I want to make it 20. Then I change this 5 to 20. Okay, it will show the FT correction factor is low, but no problem. What I want to show you is what is the approach. So now I will shift T to see the temperature. What is the approach means? So you could see it here, 35 and also 55. The difference between those stream is 20. So the approach is like the minimum delta of one stream with the another stream. So yeah, in this case, the minimum approach is 55 minus 35. It is not 168 minus 35 or 132 minus 55 or 168 minus 132.3 because this is not the minimum. So the minimum is 55 minus 35, which is 20. So if I want to make it as a 10, so yeah, you could see that 35 and 45. 60, yeah, means that it's not in this direction now. 60 is this and this, not always the same reference stream. In this case, our reference stream will be this and also this because it is the minimum delta temperature. Okay, so it's not the same with delta temperature, but because in the delta temperature, we will look at the same fluid, yeah, entering the shell or entering the tube. But for main approach, we will look at the reference of the different fluid. Okay. And then we also have the LMTD. That's also overall. Yeah. We also can spec this LMTD. For example, I want to make it 70. Yeah. We also can make it. For this LMTD, it's quite hard to explain. But you know that at least that LMTD equation is the relation between the hot and the cold stream. Yeah, in and out. For the exact formula, you can Google it. Okay, the next thing is about duty. duty is very straightforward. Yeah, so currently our duty, I want to make it overall. It's our duty is this much. Yeah. So for example, if I want to make the duty higher, 3.54E5, I will get this result. 3.7E5. Yeah, I will get this result. Okay. So I will have a more cooling effect in the hexane, but my cooling water will increase. The temperature will be increased. Okay. The next thing is flow rate. Yeah, duty ratio is actually, if you see here, duty, right? We have duty. Yeah, we have several paths between the C6 in, C6 out, CW in, CW out, and duty ratio is related to that pass here. Pass watt divided by pass watt should be how much? Yeah, for example, the C6 in and also the CW. So currently it is -1. So it means that the duty is the same, only a different direction. Yeah, negative because one of it is negative duty. Okay, so this is rarely used for duty ratio. Next thing is about flow. So if you want to specify the stream flow, we can use this. It is also rarely used. And then subcooling. So this means that if you want to make the stream subcooled by how much degrees, yeah. For example, in this case, we want to subcool the hexane, right? C6 out by how much? For example, by 5 Celsius. Yeah. So it will be 5 degrees lower than the saturated liquid. If we put it 0, it means that it will be in the saturated liquid condition. Okay, it's quite easy, right? And then superheating is the other side of this. So if you want to heat up a certain stream above the saturated vapor, by how much Celsius? So that is what it means by superheating. Okay, so you could see that there are a lot of things that we can try to spec here, and it is depends on your case. Yeah. So if you want to have a more rigorous case, which you don't want to specify the flow rate of the stream, but you want to make it calculate variables, yeah, so you can remove the flow spec and change to other spec. If you want to make the temperature is not constant, it depends on the flow, it depends on the composition. You can also put the UA, yeah, because later the output temperature will depends on the input. So yeah, that's all for this video. I hope this will be useful for you, and see you in the next Simulkuy episode. Bye bye.